My name is Jessica Todd, and I'm going to be covering the sign test and the Wilcoxon rank sum test. First, we're going to talk about the sign test. The simplest non-parametric test is the sign test. It is used for single samples. It is used to test the value of a median of a specific sample. When using the sign test, the researcher hypothesizes the specific value for the median of a population. Then he or she selects a sample of data and compares each value with the conjectured median. If the data value is above the conjectured median, it is assigned a plus sign, which is shown in my picture. If it is below the conjectured median, it is assigned a minus sign. And if it is exactly the same as the conjecture median, it is assigned a 0. Then the numbers of a plus and minus sign are compared. If the null hypothesis is true, the number of plus signs should be approximately equal to the number of minus signs. If the null hypothesis is not true, there will be a disproportionate number of plus or minus signs. As here stated, the test value is the smaller number of plus or minus signs. Therefore, if you have 12 positive signs and 4 negative signs, your test value is 4 because 4 is the smaller number of the two. We are now going to do a sample problem. A bank manager claims that the median number of customers per day is no more than 750. A teller doubts the accuracy of this claim. The numbers of bank customers per day is 16, and randomly selected days are listed. At alpha equals 5%, can the teller reject the manager's claim? Here's the list of the numbers of bank customers per day. The null hypothesis is median is less than or equal to 750, and this is our claim for the problem. The alternative hypothesis is the median is greater than 750. Down here is the chart for the numbers listed above. A plus sign is given to any of the numbers that are above our number of 750. A minus sign is given to any of the numbers in the chart that is less than 750, and a 0 is given to any of those equal to. So here's the 0 for the 750 there, and the zeros are ignored. So in that table of numbers we just had, there were 12 plus signs, 3 minus signs, and 1 0. So n equals 12 plus 3, which equals 15. The test statistic is 3 because it is your smaller number out of the minus and positive, the minus and plus signs. Then you use Appendix C, Table J out of our textbook that we use in our class. It is Elementary Statistics, a step-by-step approach, the 8th edition by Spearman. You use that table when your sample size is 25 or less, which ours is. And since x, which is 3, is less than or equal to our critical value, which is also 3, that's the number we get from our chart, then the null hypothesis is rejected. So, at a 5% level, the bank teller can reject the bank manager's claim and conclude the median number of customers per day is more than 750. When our sample size is greater than 26, if it's 26 or more, the normal approximation can be used to find the test value, and this is this formula given. And as I stated, the practice problem we just completed was 25 or less, so we did not have to use this equation. Next, we will be talking about the Wilcoxon rank sum test. The sign test that we just covered does not consider the magnitude of data. For instance, whether your value is 3 or 300 points below the median, it will still receive a negative sign. The Wilcoxon rank sum test is used for independent samples, and the test does consider the magnitude of data, whereas the sign test does not. In the Wilcoxon test, the values of samples are combined and then ranked. Each value in each sample should be ranked approximately the same. If the null hypothesis is true, that means there is no difference in the population. Therefore, when the ranks are summed for each sample, the sum should be approximately equal and the null hypothesis will not be rejected. If there is a large difference in the sums of the ranks, then the distributions are not identical and the null hypothesis will be rejected. Here is the formula for using the Wilcoxon rank sum test, and it tells what each symbol means in the equation. Thank you.
Hey, I'm Maggie, and we're going to talk about the Wilcoxon sign rank test. The example I have here is dealing with a study about the effectiveness of a new drug designed to help children with autism. A total of 8 children enrolled in the study, and the amount of time that each child engaged in repetitive behavior during 3-hour observation periods were measured before treatment and again after 1 week of treatment with the new medication. So here we've got a table with our data. We notice that over here in the first column we've got our children before treatment data, and then after 1 week of treatment of data. The first thing that we have to do is find the differences in the scores. So I've already done that for us here. Child number 1 has 85 occurrences after 1 week of meditation, 75, so the difference we have is 10. Went ahead and did that for each child. You will notice that a couple of these differences are negative. That is just because before treatment number was lower than after treatment, so they actually increased. So therefore, the difference was going to be a negative for a couple of those differences. The next thing we have to do is look at a different aspect of it and rank them. The hypothesis for the Wilcoxon sign rank test concerned the population median of the different scores. So we just took the different scores and we added those, moved them over to a different column, and then we are able to rank them 1 through 8 because once we only had 8 children, so we were able to rank them. We are going to consider this particular test one-sided rather than two-sided. The test statistic for the Wilcoxon sign rank test is defined as W. If you want to break it down a little bit further, you can have W positive, W negative. Here we expect that if the null hypothesis is true, we expect to see similar numbers of lower and higher ranks that are both positive and negative. If the research hypothesis is true, we expect to see more higher and positive ranks. So in this example, W positive would get 32, negative would get W would be 4. If you recall that the sum of the ranks, paying no attention to positive or negative signs, will always equal n times n plus 1 divided by 2, well, n being 8 because we had 8 children, 8 plus 1 would be 9, so if we say 8 times 9 divided by 2, we get 36. You always want this to equal your W, so if we take 32 plus 4, we do get 36 to make sure that that is correct. To determine the appropriate one-sided critical value, we need sample size, which was, again, sample size here was 8. And our one-sided significance was 0.05. For this example, the critical value of W is 6. And the decision rule is to reject the hypothesis if W is less than or equal to 6. Well, here our W was 4, so it is in fact less than or equal to 6. So this lets us know that we can reject our hypothesis for this study. Okay? The next thing we're going to take a look at is our Kruskal-Wallis test. The study that we are going to be looking at for this test, we're going to be wondering, does physical activity decrease depression? So we've got our data here. And if you notice, we've got 3 groups of data. We've got a group that did no exercise, the next group did jogging for 20 minutes, and our last group was jogging for 60 minutes. The first thing we had to do was rank all of these scores, ignoring which group they belong into. We put them all together and rank them. So that's what I've done here in the blue. The lowest score gets the lowest rank. So if we take a look, 22 was the lowest score, so it got a rank of 1. Moving on up, 23 got 2. If you ever have 2 or more scores that are the same, they get ranked the average. So we got up to 29 would have been the 5th lowest score, but we have two 29s. So we had to take the average of 5 and 6, so they are both ranked 5.5. It also happened again with 56. There was 2 of those. So after we have all of the ranks, we have to find what we are going to call the TC, which is just the sum of the ranks for each column. So if we add up our ranks for each column, the no exercise column got 76.5. Jogging for 20 minutes, we found 79.5. And jogging for 60 minutes, we got 144. The next thing that we have to do for this test is to find H. And H here, we've got this big formula to help us find H. If we start plugging a few numbers in, we can get part of it filled in, but then we come to this area that looks a little bit confusing. But if we notice what's on top is TC, and we have already found TC on our other chart. So we can go back to our first chart, find those numbers, plug them in, 76.5 squared over 8, 79.5 squared over 8, 144 squared over 8, and we get 4113.56. So we go ahead and plug that into our formula, and we see that H is equal to 7.27. So now that we have our H, we know that we have to look at our degrees of freedom chart. Degrees of freedom is the number of groups minus 1. We had 3 groups on that first chart, minus 1, so we have 2 degrees of freedom. So we're going to just pull the part of the degrees of freedom chart that we need, and we are able to see that if we have more than 5 participants per group, then H is going to be a chi-square. H is statistically significant if it is equal to or larger than a critical value of the chi-square for our particular degrees of freedom. Here we're looking at 2 degrees of freedom. So I have gone ahead and drawn a box around this row because this is the only row we're looking at because we have 2 degrees of freedom. So if we move along the chart, we start by comparing our H of 7.27 to 5.99. With 2 degrees of freedom, the chi-square value as large as 5.99 is likely to occur by chance only 5 times in 100. So our obtained value of 7.27 is larger, so we're going to keep moving. Our H will occur by chance with a probability of less than 5 in 100. So moving across the chart, we compare it to 9.21. That will occur by chance 1 in 100 times. So, with our H being right in the middle, it is going to be less than 9.29, more than 5.99. It tells us that our H value is not so large that it is likely to occur with a probability of 0.01. It will occur somewhere in the middle here. So, if we want to take a look at all that data back on that test, we can conclude that we found purely by chance they're somewhere between 0.05 and 0.01, so it's pretty unlikely, and we would conclude there's a difference of some kind in our 3 groups. However, the Kruskal-Wallis test merely tells you that the groups do differ in some way. It does not tell us how they differ. So, in this particular case, it's fairly simple that we can determine that exercise does seem to alleviate depression, but only in those who exercise for at least an hour. The 2 groups, no exercise and jogging for 20 minutes, they hardly deferred at all. So for this particular study, we can decide that exercise will alleviate depression in those who exercise for at least 1 hour.
Hello, I'm Toya Howard, and today I'm going to talk to you about the Spearman rank correlation coefficient and the run test. Our example for the Spearman rank correlation coefficient is I have 4 NBA players, and we're going to list them as A, B, C, and D. And we're going to take their points or their scores for the year 2013, and we're going to compare the scores, or we're going to rank them. And so player A, we have, he scored 529 points. Player B scored 683 points. Player C, 450 points. Player D, 600 points. We're going to compare that with the scores they scored for 2014. A scored 500 points. B scored 485 points. C, 630 points. D, 615 points. So our formula is P equals 1 minus C with the sum of D squared over N times N squared minus 1. So in order to find D squared, which is the difference between each player's points ranked, is the difference. Player A in 2013 ranked 3rd place, B ranked 1st, C 4th place, and D 2nd place. In 2014, A remained the same in 3rd place, B went down to 4th, C went up to 1st, and D remained in 2nd place. So the difference between the ranking is player A, there was no difference. Player B, there was 3-point difference. Player C, 3 points difference. And player D, 0 difference. So we take those differences and we square them. And as we square them, player A has 0 squared, which is 0. B has 3 squared, which is 9. C has 3 squared, which is 9. And D has 0 squared, which is 0. To find the sum of D squared, we'll add all the D squared together, which is 18. So our formula, P equals 1 minus 6 from b squared over n times n squared minus 1. So when we find the subsquare of 10 squared, b squared, excuse me, we have 1 minus 6 times 18 over 4, which is our category of people that we had. So we had 4 ball players, so that's the number that we have, that's 4. So then we square 4, which is 16 minus 1. So we're at 1 minus 108 over 60. And then to reduce that is 1 minus 1.8. So our P equals negative 0.8. And so because we have a negative 0.8, there is a substantial negative correlation in which our graph will be somewhat like this. So that's how we do our Spearman rank correlation, by ranking our group. Now we want to discuss the run test. In the run test, I'm going to use the same for NBA players. Each player scored either a 2-point or 3-point shot. Our critical value is 0.05. Is it random? So player A has 2-point shot, 3, 3, 2, 2, 3, 2, 2, 3. B has a scores of 3, 3, 3, 2, 3, 3, 2, 2, 3. C has 3, 2, 3, 3, 2, 2, 3, 3, 3. And D has 2, 2, 3, 2, 2, 3, 2, 2, and 3. And in order to know if they're random or not, we go by to see if they are random. Is A the way it is it random? It's not a pattern, so no, it's not random. B is not a pattern, so no, it's not random. C is not a pattern, so no, it's not random. But D is, it has 2, twice, 3. 2 twice 3, 2 twice 3. So we want to know, is it random? So in order to find out if it's random, we must do a run test. First, we must find our null hypothesis, which would say the point is independent from the previous point. A sub 1, which is our alternative hypothesis, is that the point is not independent from the previous point. So then we want to find n, which is the total sample. N sub 1 is the number of observation of one type, and n sub 2 is the number of observation of the other type. So going back to the players to find the run test, we have the players again. So player A, we want to find n sub 1, and n sub 2. So we're going to find n, and that is the total sample, so of the run. So here we have, that's one run. The underline and orange are the different runs. So we have different runs here, and it's a total of 23 runs. And our n sub 1, that's going to be 2-point shots. So everything that's in green, which is the number 2, those are n sub 1, and that totals to 17. Our n sub 2 is in the purple, and so that is the number 3. So therefore, we have every 3 that we have, that goes in our n sub 2, and that's 19. And so now we know that our mean is 18. But so once we get all of that information, we go and we look on table M to find the critical value at 0.05. So once we go to table M, our n sub 1 is here in our far right corner, and then our n sub 2 is at the top. So then we go down, and our n sub 1 was 17, and our n sub 2 was 19. So we come together and bring them down, and we're in the points between 12 and 26. So since our run does not exceed or is less than our critical value, which is 12 through 26. Our N is 23. Our run is between 12 and 26. Therefore, we will not reject it because 23 number of runs fall in between our critical value. We would reject the null hypothesis if the number of runs were less than or equal to the smaller value or greater than or equal to the larger value. So therefore, we will not reject our hypothesis because 23 is in the middle of 12 and 26. So that is our Spearman rank correlation and our run test. Thank you.